rhythm, essentially we're back to our poetical meters again. So, except we have 2 beats, and tend to have 2 beats per bar sometimes. But really you're looking at the same, a complicated longer version of your poetical feet, and I'm not going to slow it down, let's move on. Melody, I think we can say some interesting things here. And some of the things we can say is that melody is very closely related to rhetoric. It has the same quality, it's the same feel. It's something that's evolving in time. It has shape, a melody. It has rules as well to do with the chords you're playing. Those are really harmonic rules. Let's look at the melody itself. And, they're really, the main chord progressions aren't huge numbers of them that we use. But essentially we've got this thing of rising and falling, something that you get in melody, and something that we hear in our cadence as well, in the way we speak, things going up or down. And you have pattern, and you have this very important thing of repetition. Repetition obviously being a key of another component which I'm not going to talk about today, which is symmetry. Often missed out completely from the class. Symmetry is a core component as well of liberal arts. It's quite hard where to place it because it's happening everywhere. Really, happy birthday to you, happy birthday to you, happy birthday. You've got a pattern that's repeating. If you listen to melodies, most of them have these repeating qualities. And then there are different ways in which things can repeat. They can reflect, they can translate, they can rotate, they can get bigger or smaller, they can branch. So lots of different kinds of repetition. They can change in strange, in different ways. So lots of different kinds of repetition, and then you have the different sounds themselves that compose the orchestra. So really that's the elements of music in a nutshell. I'm trying to do all that first, obviously, very quick nutshell. And then we've got geometry, which begins with how big things are, the lengths, size of the earth, and things develop from the circle, from the lines and angles and shapes, and squares and triangles, and we have our geometric proportions, which are different to our harmonic proportions. Our harmonic proportions are all ratios, aren't they? Simple ratios. Our geometric proportions generally are the square roots of simple numbers. Square root of 2, square root of 3, square root of 2 comes out squares, square root of 3 comes out triangles, and then we've got our 3-dimensional solids, 5-dimensional solids, and in particular these 2 complicated ones, the icosahedron and dodecahedron, both of them have pentagonal geometry, and pentagonal geometry uses the square root of 5 as well, which brings in a portion into the golden section. So I was going to whiz through these because these are our regular and semi-regular grids, tessellations of simple solids. They're, if you like, the flat equivalent of the sonic and Archimedean solids. And then we've got more bits of symmetry and geometry being used by artists. I always think geometry is more physical than music. It gets more widely used in the physical world. We're beginning to get into the physical world with geometry. It needs to be drawn on paper. So these are square root of 2 portions, which is the A series paper. Fold it in half, you get the same rectangle. And here's the golden section, pentagram. And the golden section rectangles surround us and are widely used by artists and designers to this day. Very interesting diagram is popularised by Malcolm Stewart. It's called Sandringer's diagram. Very easy way of dividing a piece of paper or anything. It's a 3s or 5s at the end there. You just draw the diagram at the top and just look at where the lines cross. And just track it down below the inch as well. So it's a really good trick. You can get 7s out of it. By any line, 7, 11, 17, or whatever you want using it. So and geometry goes right back. Use of geometry goes right back into antiquity and beyond into ancient history. It's stone circles all over Britain using the same principles of geometry that are then later used throughout the Christian and Islamic worlds. Those are British stone circles laid out using geometry. In fact, the same kind of geometry is used to do Islamic domes because of branches. And not quite so much, but they are. And modern geometry, probably the best example, or most exciting, I think, was the Penrose tilings that popped up in the 1970s, where Roger shapes that you could basically put together, and they would create, they tile a plane, you could tile all the way here, from here to the United States of America, but the pattern would never repeat. Quite amazing, just with two shapes. And modern architecture tends to use huge amounts of geometry, obviously, as we get computers to do the hard work for us, and the geometry is then incorporated into small and small bits that tend to be cut up by machines. So geometry is still at the heart of our built world, but not in such obvious way that it used to be. And here's the final section on astronomy. Well done for hanging in there.
Well done you.
All right. So astronomy is, I always call the astronomy the poster boy for the physical sciences. So the 7 liberal arts led us up to this. So we've been studying non-material stuff, but I do think astronomy is beginning to be, it's the poster boy in the sense that it's quite useless studying astronomy because you can't build anything with it. But essentially we are getting into physical sciences a little bit. We're looking at the real world at least. And we've got things like gravity and what to include in the physical sciences, the physical forces, gravity, electromagnetism, and we've got geology and earth sciences, and here's astronomy proper. All those things come to bear when we turn telescopes and look at the living world as well. That's all part, in my opinion, of astronomy. But classically, and life study what makes so we just want to run through the physical sciences. We've got the geometry of the embryo, we've got zooming in, we've got DNA inside that, zooming in, we've got all these molecules that we really understand very well now, and chemistry and physical sciences, and zooming in, we've got molecules and atoms, and zooming in those, we've got our quarks, and zooming into the quarks, we've just got energy and light. And light is at the core of the old idea of the ancient idea of the cosmos as being essentially a living, conscious entity. In many religions, that being personified as the sun, as a living entity, and the moon and the sun and the moon are the same size in the sky as viewed from the surface of the Earth at this time in human history, which is quite an amazing coincidence and well worth thinking about. This means that they can eclipse one another, and of course the study of that goes way back to antiquity as well, with Stonehenge being able to use, whether it was not that you could use Stonehenge to predict eclipses very accurately, and the fact that Göbekli Tepe, the site on the Syrian Turkish border, it's being excavated, we can show as well that astronomers we're studying precession. You can see that they're studying precession very clearly because they're looking at the night sky, and if you look east and you had a long exposure, you'd see the stars doing that, and if you look north, then you see the stars doing that. And what they realised at Göbekli Tepe is that they're watching Sirius rising and setting, and it's rising and setting differently at the end of their lifetime than it was at the beginning of their life. So it's normally the stars going to be popping out of the ground at the same point every day. But over 70 years, in fact, the stars move at 1 degree, rising and setting positions. In fact, that would puzzle the early astronomers, and it looks like the earliest building on the planet was built as that's to do with the Earth spinning like that, another lunar cycle, and precession, and it looks like they were studying that. The earliest building we've got seems to be an observatory. And of course we've got the Zodiac, that goes back much even earlier than that. We've got the Zodiac after Göbekli Tepe as well, which is quite incredible to think about. And then you get the lovely medieval, you've got the solar system, which is the basis of medieval cosmology, with Earth in the middle, and then the planets are arranged always in their order of speed outward. It goes Earth, then the Moon, then Mercury. What's that? The Moon in one place. What's that there? Layout, I don't know what's supposed to be on fire, I'm not sure. Oh, I see Earth and water, and then air, and fire. And then it's Moon, Mercury, Venus, Sun, Mars, Jupiter, Saturn, and then sometimes there's 4 outside that. So whenever you see the curves of a cathedral door, they're always like that, which was the Ptolemaic universe of antiquity, these cycles and epicycles that actually give the the patterns, the wonderful Steinberg, Joachim Schultz's book, Movements of the Planets and Stars, recently republished by Floris Books. Fantastic book. The first place I ever saw these epicycle drawings reproduced really beautifully. And of course, the Ptolemaic universe worked so well that you can build your clock. There's the actual kind of theorem mechanism that we dug up in the discovered 1901, that's right, but I think no one really understood what it was. It's a full working clock, and it showed where all the planets were. And in the same way, you could use the Mayan calendar. In fact, the Mayans were up to the same thing. A different system using lots of 13s. Essentially, the Mayan calendar you could build. This is a construction I did with a chum, Jeff Stray, and he showed that you could basically use it. You put the Mayan calendars completely together as a full working clock of the solar system with fewer cogs than the Ptolemaic one. And you get systems like Kepler's. So we're always trying to understand the heavens, and we're trying to simplify them all the time. Is Kepler's idea of sonic solids separating out heavenly spheres. And that's some work I did some years ago, trying to pick up Kepler's idea to see if they worked. Is Mercury and Venus the first two planets showing their average orbits being created by putting three touching circles together. And other work I did on the same line came down to try and find here a pentagrams showing Earth and Mercury's orbit, here relating to the global section, and the sizes of Earth and Mercury, different planets relating. And of course here's the classic Venus Rose diagram, which is it's come out a bit, got some errors, but that's quite a recent plot I did of it, where you've got our closest planet Venus, and we're essentially standing on the Earth. So it's a geocentric view for those that don't know. And we're looking at the sun, and there's the sun that's going around. And Venus is in between the sun and us doing this, and of course the sun's going round. What's happening is Venus, our closest planet, is drawing this beautiful pattern over 8 Earth years, quite accurately. Those 8 Earth years are very interesting because they're also 13 Venus years. So 8 to 13 is what gives you the 5. And the other thing about 8 years, relating to that with the piece of music we heard at the beginning, is that over 8 years, almost exactly 99 full moons. So when you see the Islamic thing with the moon and the star, what you're looking at is a depiction of this 8-year cycle with those 99 moons. So if you saw the moon Venus like that, after 99 moons, you would see it again. And this 5, 8, 13 is very interesting. So you've got 5 with 8 years, over 13 Venus years, 8 Earth years. And of course, all life on Earth is doing 5, 8, 13 as well, which is a very lovely thing. And of course, the universe is very big, and we are getting to understand more and more of it all the time at the moment. So we've now mapped 10,000 other solar systems, and that is expected to go up to 1 million other solar systems in the next 4 years. So it's an unprecedented time right now in our understanding of astronomy and how unique we may or may not be. We do seem to be quite unusual, like it's the latest thinking. This is the best contender for extra-planetary life so far discovered, which is called the TRAPPIST system. The TRAPPIST system is very interesting. It's a mini system. It's like a bonsai, like quite big Earth-sized planets, but they're being placed together and they're going around a very small star, white dwarf star, and the TRAPPIST planets are in periods 1, 2, 3, 5, 8, 13. So it's a Fibonacci system, Fibonacci tune, and in fact, if you plot the TRAPPIST systems, it's the number 1 contender for life, according to NASA. If you plot its planets there, you stand on planet B, then both planets D and F are producing rosettes around you, which is quite extraordinary as well. And thanks so much for everything. I'm so sorry I went so long. All I could do it now is just no way.
I'm sure there were lots of questions which we're going to have to wait to the plenary because, clearly, it's a tall order to speak on liberal arts, and I think, you try to just bring so much in. So thank you very, very much. So I think we'll have to sort of see how we're going.